Hello everyone, my name is Devendra Kapadia, and in this two-part presentation, Oliver Rubin Koenig and myself will give you a fairly thorough introduction to solving partial differential equations in the Wolfram language. Oliver and I both are members of the kernel development group over here at Wolfram Research, but we have slightly different interests. I'm a mathematician and I work on symbolic solutions of differential equations, while Oliver has an engineering background and works on numerical solutions of differential equations. So I'll go first and speak about symbolic solutions of partial differential equations, and then Oliver will come in and speak about numerical solutions of PDEs using the finite element method. So hopefully between the two of us, we'll give you a pretty nice overview of the whole field. Okay, so here is a more detailed plan for my talk. So I'll begin with talking about first order PDEs, and I've chosen the transport equation, the scalar conservation law, and the Claro equation to illustrate this class of PDEs. And it will be clear to you that even these first order PDEs offer a lot of complexity. Now, if this were a course on partial differential equations, it would be very important to talk about the classical PDEs. So I'll also talk about the classical PDEs, namely the wave equation, the heat equation, and the Laplace equation. Now, the field of PDEs has continued to evolve into modern times, so I've chosen 4 modern PDEs for today's talk, namely the Burger's equation from fluid dynamics, the Black-Scholes equation from finance, the Schrdinger equation from quantum mechanics, and finally the KdV equation from solid-atom theory. Now, at the heart of many solution techniques for PDEs are the so-called Sturm-Liouville problems, which are basically eigenvalue problems for differential equations. And so I'll show you how to solve these with dsolve. But in practical applications, it is often more convenient to work directly with the eigensystems of a differential operator. So I'll do that using the d-eigensystem in the last part of the talk. Okay, so let's begin with the first order PDEs and the transport equation. So transport equation is an example of a linear first order PDE. Now, you can find a general solution of this equation with dsolve, and what you get back is a traveling wave kind of solution, but this over here is an arbitrary function in the general solution. So to find a particular solution, what you could do is to give an initial value, and once you've done that, then you get back a particular solution of the transport equation. And finally, what you can do is you can animate the solution in Mathematica, and you see that this is wave traveling to the right. It's a very simple kind of solution, but the transport equation itself is quite fundamental to the whole area. Okay, so now I go on to scalar conservation law. So the scalar conservation law is a quasi-linear first order PDE. So this over here is the quasi-linear term. But even in this case, if you try and find a general solution, you get it back in implicit form. And that means that in general, it is rather difficult to solve the scalar conservation law and get particular solutions. But you can do it, for example, with this very simple set of initial data. And then you get back a simple solution of the scalar conservation law. And finally, we go on to the Claro equation, which is an example of a nonlinear first order PDE. So that's the Claro equation. It's got 3 terms, x times a first partial derivative, and then y times another partial derivative, and that is the nonlinear term. Okay, so it turns out that for nonlinear PDEs, the best kind of solution is a so-called complete integral. So let's find it over here. And dsolve complains that this is a nonlinear PDE, so it is trying to build a special solution. And this special solution is based on parameters C1 and C2. It looks rather simple, but then remind yourself that in fact this is a 2-parameter family of planes. And so what you could do is you could actually let's say fix C1, and then let C2 be a function of C1, and what you then get is a one parameter family of planes. And then the envelope of this one parameter family would be another solution for the PDE. So let's see that geometrically. So the animation shows you over here now that the orange planes kind of rotate to give you the envelope solution. And this is exactly how DSolve solves the initial value problem over here, and you get back a particular solution. Okay, we now move over to the classical PDEs, and let's begin with the wave equation. So the wave equation is an example of a linear hyperbolic equation. What that means is it's really good for studying the propagation of signals of all kinds. And in particular, if the signal has a discontinuity start, then that must be propagated all the way. And to see that, let's look at a plug string over here. So for the plug string, let's say we assume that both ends of the string remain fixed during vibrations. That's a good assumption. We then pluck the string, let's say 1/3 of the way from the left. And once we've done that, we let the system go, and DSolve can then solve the wave equation with these conditions. Now, there are many available techniques in this area, but for this particular example, DSolve chooses the separation of variables method because that gives a nice textbook-like solution to the problem. But it is a rather difficult integration, so it does take a bit of time. But when it's done, you'll see you get back an inactive sum, an inactive infinite sum, in fact, of elementary solutions of the wave equation. So this solution is what we can then use to study the plug string in greater detail. So there's a solution over there. You can pick out, let's say, 100 terms from it, and then you can visualize the vibrating string with an animation. So that is the animation for a vibrating plucked string. Now notice that although this is a hard problem, the symbolic solution is a very complete solution, gives you lots of information, and therefore is pretty useful in this case. Okay, so I now go on to the heat equation. And the heat equation is an example of a parabolic PDE. Now, roughly speaking, that means is that this equation is going to smear out information. It's going to make things smoother and nicer as time goes by. And to see that, let's consider the case of the flow of heat in a bar that is insulated at both the ends. So let's specify first that no heat flows to the ends of the bar. And next, let's give an initial temperature at different points on the bar initially. So let's say when x is 0, then the temperature is 20. When x is 1, the temperature is 100. And then you solve the heat equation with these conditions. And again, the choice of method over here is the separation of variables. So you get back an infinite sum of solutions. You pick up, let's say, the first 10 terms over there. And then finally, when you visualize it, you see that that is the initial data over here. And then very quickly, the solution settles down to its steady state value of 60 degrees. So the heat equation is quite important in all kinds of applications. And finally, the Laplace equation, which is used to study steady states basically. So that's the Laplace equation. I give a Dirichlet condition on a rectangle. And then what I do is I use DSolve and separation of variables to solve it. I, let's say, pick out the first 300 terms. And then we visualize the solution on the rectangle. And there are some remarkable features of the solution. The first point is that the Dirichlet problem over here is well posed. There is a nice solution to it. And that itself is a hard mathematical theorem. Next, although the boundary conditions are kind of sharp and have sharp features, the solution itself is nice and smooth. So that is a particular property of these so-called elliptic equations. And finally, notice that the extrema do not occur in the middle, but they only occur at the boundary, and there's a saddle point in the middle. So this is another nice feature of elliptic equations. So the Laplace equation is important from a conceptual and practical point of view. Okay, so I now move on to modern PDEs, and let's begin with the Burger's equation from fluid dynamics. So the Burger's equation was proposed around 1940 as a model for turbulence. So this is the Burger's equation. The epsilon over here is really the viscosity for the fluid. And when Burgers proposed it, he hoped to provide a very simple model for turbulence. Now, if you propose a model for turbulence, the last thing that you want is for someone to tell you that your problem has an exact solution. And that's exactly what happened 10 years later. Hopf and Cole showed that the Burgers equation could in fact be reduced to the heat equation by transformation. So let's see this remarkable solution with some piecewise data over here. And when you solve with dsolve, in fact I'm using dsolve value over here because that's a little easier to look at in terms of solutions. The solution comes from a rather difficult integration, but the error function over here, the ERF, tells you that we really have a heat equation kind of solution. And the nice thing is that this solution is smooth for any positive value of epsilon. On the other hand, when you start passing to 0 and make epsilon smaller, then you do see a shock discontinuity developing, as you see over here. And that is a typical feature of these nonlinear PDEs, that you can have shock phenomena occurring in some limiting case. Okay, so I now go on to the Black-Scholes equation, which was proposed by Black and Scholes in 1973 as a model for option value financing and prescription in finance. Okay, so Black and Scholes realized that their equation too could be reduced to the heat equation. So when you solve this equation in Mathematica, you get back a solution, and that solution has got, again, error functions inside it. What you could do now is to actually give some particular values to the parameters and get back an option price. And just to make sure things are okay, you give it a financial derivative with similar values, and you get back exactly the same answer. So at least to me, it's rather remarkable that such a closed form symbolic formula has got so much importance in a very practical applied situation, and even more that it all comes from the simple heat equation which we looked at early on. Okay, now in modern times, the Schrodinger equation has acquired a lot of importance because it models quantum mechanics. So in fact, over here, we have the two-dimensional Schrodinger equation for a quantum particle free to move within a two-dimensional rectangle. There's a mysterious I over there, which plays a big role in solutions. So what I do is I prescribe some initial conditions. In fact, over here, I've got a sum of states as initial condition. And then what I can do is prescribe boundary conditions to say that it's all 0 at the boundary. I solve the boundary problem. And all that happens over here is that the initial states kind of get mixed up, so you have some kind of entanglement taking place. Now, it's rather difficult to work with these complex valued solutions. So Max Born taught us that in such a case, what you do is move over to so-called probability density to actually get some kind of physical picture of what is happening. So that is the probability density row, and you can visualize it using plot 3D. That's a hard animation, but it will come up in just a minute. And when that happens, you see that the particle wanders all over the box in some kind of non-deterministic manner according to Schrodinger equation. So that's a very pretty picture based on some work done by my colleague Itai Segev. Okay, as a final example of a modern PDE, let's look at the KdV equation, which is a nonlinear PDE. But the remarkable thing is that this PDE is in some sense completely integrable, which means that one can find lots of solutions of the equation and they have some remarkable properties. So for example, dsolve can find so-called triangular solutions of this equation. So again, it complains that trying to build a special solution, and the special solution has got parameters C1, C2, and C3 in it. What you can then do is you can obtain a particular solution by giving values to these constants C1, C2, and C3. Now this over here is a rather remarkable particular solution. So historically, in the year 1834, the engineer Scott Russell was riding his horse along the Edinburgh Canal, and he noticed a kind of solitary wave which was moving along. He chased it on horseback for about a mile and then lost it in the windings of the canal. He came back, wrote up his work, and what you see over here now in the animation is exactly the kind of wave that Scott Russell saw on that day in 1834. So these solitary waves are absolutely crucial for many applications, and I believe that the last word on them has not been said as yet. They will continue to be important in the future as well. Okay, so now we go a little deeper into the so-called Sturm-Liouville problems. So in the 1830s, the French mathematicians Sturm and Liouville started looking at qualitative theory of differential equations. So they were not really interested in solving a differential equation, but trying to understand some general features of a differential equation. So as an example, what they did, here is a so-called Dirichlet problem for this rather simple equation, y double prime plus lambda y equal to 0. Those are Dirichlet conditions. They just say that the function y is 0 at both the ends. And if you ask DSOLVE to solve the problem, it tells you that there are solutions, there are non-trivial solutions only for a very limited number of values of lambda. Namely, lambda had better be a perfect square. So here are the first 5 eigenfunctions, sine x, sine 2x up to sine 5x. And then what you can do is you can plot these eigenfunctions. So the Dirichlet problem is a very simple example of a Sturm-Liouville problem. Now, you could also prescribe derivatives at both ends. That's a so-called Neumann problem. So here I say that y prime is 0 at both the ends, and you get back a solution in terms of cosine. Again, you can find the first 5 eigenfunctions. So the one over here is, of course, also a solution in this case, and you can plot them. So those are 2 basic eigenvalue problems for differential equations. Now, slightly harder than that is the so-called Robin problem, where you have a combination of derivatives and values at one or both the ends. So if you give it to DSOLVE to solve in this case, what you notice is that the eigenvalue equation is a transcendental equation, so it's quite hard to solve it in general. But what you could do is to give a specific range to the parameter lambda over here. And when you do that, and do, let's say, a plot of the type over here, notice that the eigenvalue equation has roots somewhere close to 4 and close to 8. The question is, how do you obtain this solution using DSOLVE itself? Well, it was for this purpose that we have the assumption option. So if you tell DSOLVE, find the eigenvalues and eigenfunctions in that particular range, then it does come back with an answer. But what you see over here is this root object, which looks a bit strange because it's got an inexact number in it. And one has come to believe that DSOLVE and DSOLVE value both work only with exact answers. But in fact, these eigenvalues are really exact, and you can work out, let's say, the first 10,000 place of decimal in this case quite quickly. So what you see over here is that we have a very complete solution to the Robin problem obtained by specifying a range for the eigenvalue parameter. So Sturm-Liouville problems, of course, foundational, very important, but in practice, you really want to have only a few eigenvalues and eigenfunctions, and so we now talk about so-called differential eigensystems. And in fact, the d-eigensystem function, which was introduced recently, does just that for you. So for example, suppose I want to find the first 4 eigenvalues and eigenfunctions of the Laplacian with Dirichlet conditions, then d-eigensystem does that for you in a flash. You get back the eigenvalues of 1, 4, 9, and 16. You get back the eigenfunctions, And then you can visualize the eigenfunctions just as before. And it's a very nice application of the eigensystem. Let's look at the quantum harmonic oscillator. So the quantum harmonic oscillator is very similar to the classical oscillator, but the eigenvalues and eigenfunctions are now much more fundamental. So here's the first few eigenvalues and eigenfunctions obtained with the eigensystem. So that's the ladder of eigenvalues. You can climb the ladder from left to right. Now, that's all very static. So what you could do is to breathe some life into it with some time dependence, which is what I do over here. Then again, we follow Max Born and move over to the probability density. And having done that, you can then visualize the probability density over time. So that is a quantum harmonic oscillator solved using version 11. Okay, now beyond ODEs, there are very nice eigensystems for PDEs, and particularly for the Laplace equation, for the Laplace operator. So here is the Laplacian in a rectangle. You have Dirichlet conditions. I look for the first, let's say, 8 eigenvalues and eigenfunctions in the rectangle. That's the rectangle over here. And then I look at the values which are integers. And you notice there's some redundancy over here, some degeneracy over here. And those are the eigenfunctions, which are basically kind of products of eigenfunctions for the 1D Laplacian. So what you can do is you can then visualize them, and you get back this very pretty set of eigenfunctions for the Laplacian in a rectangle. You can also do the same thing for, let's say, a cylinder. So that's the Laplace equation, the Laplace operator in a cylinder of radius 2. And next what you can do is you can ask for the eigensystem with the first 7 eigenvalues, eigenfunctions. The eigenvalues in this case are in fact zeros of Bessel functions, as you can see over here. And the eigenfunctions are combinations of Triggs and Bessel functions. Now, we have a very nice new function which is recently, that's density plot 3D, which gives a very pretty picture of, let's say, the 7th eigenfunction. So let's just wait for that to come up over here. But what you get back is a very pretty eigenfunction for the Laplacian in a cylinder composed of Triggs and Bessel functions. And as my final example for today's talk, I'm going to talk about the vibrations of a circular drum. Now, that's a well-known problem, but typically what you talk about is the case where you hit the drum right in the middle. So a few weeks ago, John Snyder, who's an expert user of Mathematica, wrote to me to say that in fact he had solved it for the case where you can strike the drum at somewhere between the center and the periphery. So John's method is to start with the Laplacian in 2D with the Dirichlet conditions on a unit disk. And then having found the eigenvalues and eigenfunctions with Bessel zeros and Bessel functions, he then evolves these eigenvalues and eigenfunctions in time, and using the first 128 eigenfunctions and some very nice smoothing properties, he actually managed to get a beautiful animation of a circular drumhead when it is struck off the axis somewhere near the boundary. So let's run the animation over here. This is absolutely remarkable, at least to me. So here's the animation. You see that's the circular drum which has been struck off axis. So this tells me that really the eigensystem is a very successful function. It can show you this very detailed, intricate behavior of something as simple as a circular drum. Okay, so I'm really at the end of my presentation, but just to give you a hint of what's going to come in the future, well, we are working on integral transforms. In fact, at the moment, we're working on the Hankel transform. And we also would like to have some more support for green functions in PDEs. So that's a set of directions which is kind of very mathematical and important for the future for symbolic solutions of PDEs. On the other hand, for applications, we also need to support periodic boundary conditions which are important for many applications, and other geometric regions beyond just the ones we support now. But luckily, in both these cases, Oliver has done a fantastic job of providing support in D-eigensystem and in D-solve. So at this point, I'll conclude my talk and hand over to him. It's been a great pleasure to speak with you, and I'm really excited to have been able to show you all this wonderful functionality in version 11. So at this point, I'll stop, and thank you very much.